Guys and girls, welcome back to another Space Explorer episode. Today's guest is a phenomenal one. You're going to see her in a few minutes, but let me firstly introduce you to her. Her name is Stella Kafka. So Dr. Stella is the Executive Director and CEO of the American Association of Variable Star Observers, an international organization focusing on engaging professional and amateur astronomers in science. So within the auspices of the AAVSO, Dr. Kafka is working towards enabling individuals from all backgrounds to actively participate in research projects, building a diverse and inclusive community of science-savvy citizens who work collectively to understand some of the most dynamic phenomena in the universe. So Dr. Kafka acquired a bachelor's degree of science in physics from the University of Athens, that's in Greece, and her master's PhD in astronomy from Indiana University in USA. So Dr. Kafka researching interests are semi-detached binary star systems. It's called cataclysmic variables. Sounds pretty scary, but let's talk about that, of course, as well, which can become supernova. So, of course, you will find in the show notes a couple of links, LinkedIn, Twitter, Instagram, and you should go and connect with Dr. Kafka and ask her questions, anything we didn't cover in the show. So very happy to have you on, Dr. Kafka, and thank you so much for your time, and it's greatly to meet you.
Thank you for having me. It's a privilege to be here.
Thank you as well. Thank you. Again, a big shout out to Rod Stubbings. I don't know if he's going to be watching this episode. I kind of, he made the connection. I really appreciate him for doing so because, first of all, I have to tell anybody with the name Stella, which again, it means Latin star, is probably destined to work in the science field, right? And especially with you, variable stars and the name Stella, it just matches in a great way. So could you please tell us a little bit of your own background? Can you kind of tell me you went to the United States about a century ago, and so how do you feel like your journey entire? Where did it begin? Where did you get this bug for the for the science and working in this particular field? And can you talk about your kind of day-to-day routine right now, what you're working on?
Absolutely. So let's start from the very beginning. I was born in Athens, Greece, last century, which sounds very far, far away. And it's even worse when you think that it's also last millennium. And I grew up in Greece as well. I finished my high school, middle school, high school education there, and I went to the University of Athens for my bachelor's degree. Astronomy was not a major part of my life growing up, simply because I grew up in a big city, a big light polluted, you name it, city. Mm-hmm. However, physics was always part of who I was. I was always curious to see how the world around me works and what the world is made of. And it's this natural curiosity of the first explorers, right? You look around, you break things in the way, you figure out how they work, and then you look up and you wonder whether you're alone in the universe. So one of the milestones in my life, I was actually at the university where this happened, is I was part of the amateur astronomy club in Athens, and we were looking at the moon. I wasn't interested in the moon as much, but we're looking at planets. When you see Saturn the first time from a telescope, you think it's a postcard, right? Somebody put a picture on the other side of the eyepiece, and you're just looking and try to figure out whether it's true or not. But it's so spectacular, so beautiful, so majestic that it really captures your imagination of how it looks like. So even as an undergraduate at the physics department of the University of Athens, I actually did my undergraduate thesis in astronomy. And I remember my undergraduate thesis advisor, Dr. Mary Contizas, telling me that, something, there's no turning back once you go with astronomy. And, she was so right. After that, I came in the United States last century, as you mentioned, the end of the 1990s. And I went to Indiana University for my PhD. The reason why I chose IU Bloomington was because it was a small department, so I could get a lot of attention from my advisor. I could just learn from him. And also it had time on a 3.5-meter telescope in Arizona. I wanted to be an observer. I had to learn how to observe, right? And actually going there and looking at the night sky for the first time was a scary experience. I saw the Milky Way for the first time in my entire life, and I thought it was a cloud. I thought it was like a rain cloud. And I remember my thesis advisor saying, no, that cloud's going to stay there. And he's still joking about it every time we reminisce of the good old times. But I really benefited from the encouraging environment of that university and that department, who was actually, it consisted of individuals who were young in mind and heart, curious, and really allowed us graduate students to pursue the research we wanted. So my thesis advisor really encouraged me to follow the data, right? Whatever results we were coming up, we're just going after it in principle to learn something in a guided way, right? I had to actually get a PhD at some point. I could not retire as a graduate student. So after Indiana, after I got my degree, I went to the Cerro Tololo Inter-American Observatory in Chile. That was a fellowship, so I could do my own research. And at the same time, I was the site director of a program that was funded by the US government. And I was bringing students from the US to the observatory in Chile for 10 weeks in the Chilean summer, so backwards from the Northern Hemisphere, to do research with researchers. So as a director of that program, I had a chance to, put a little bit of my flair in it and change it a little bit, make it a little bit more aggressive for the students, so that they could understand science literature and do their research and visit other observatories while they were actually working on their projects. And I really had fun. But at some point, this was a limited time position, so I had to look for my future. And I had an offer to go to Caltech at the Spitzer Science Center when that lovely satellite was still up there, taking data on the dark side of objects. It was like a little bit outside our visual spectrum. And actually, I was working on the same objects that I was working before, cataclysmic variables, but at a different wavelength range. So I had a chance to play a little bit with satellite data, see a different astronomical community. And again, at some point, there was a limited time position. After that, I wrote a proposal at the NASA Astrobiology Institute, and I got a fellowship with them, a 3-year fellowship, which I took at the Carnegie Institution of Washington. So from California, I jumped all over to Washington, D.C., where I spent 3 years. From there, I went to the American Institute of Physics, something completely different, work with scientific publications. Science is science, and as physicists, we have all kinds of interests. But at the same time, while I was there, and actually I was really having fun, a position opened here at the American Association of Variable Star Observers for an executive director. And what they were looking was for a person who had management experience, but also knew the field of astronomy, the specific field of astronomy that the AAVSO is involved with, meaning variable stars. And we can get into what variable stars are. And it turned out it was a perfect match, because when it comes to science, I am a daughter of the AAVSO. I used the AAVSO data for my PhD thesis. I knew what AAVSO observes. Of course, I know now what they're capable of doing, what kind of contributions they're making to science. So it turned out that it was a great match. So in 2015, I started my tenure in February 2015. I started my tenure here in Cambridge, Massachusetts. So it turns out that every time that I move, I go to colder climates, but still, it's been a very rewarding path so far. I've been having a lot of fun, and also, work hard, play hard, right? I feel that I'm serving a very active and very passionate community of individuals who are trying to make a difference in the world, in the science world, by contributing data, analyzing data, understanding data, and also opening astronomy does not have borders, right? Opening the world of science to individuals who want to be involved in it. Astronomy is the only science where individuals without a formal degree can make meaningful and actually impactful contributions to science.
Yeah.
So here I am. And I'm
That's
waving
good.
at you and Rob from Cambridge, Massachusetts.
Here you go. Here you go. So that's beautiful. I mean, that's a beautiful journey that you took on, and the experiences that you had. I'm pretty sure there's countless of great stories that you can tell about that as well. So, but I want to ask you about AFVCO. I don't know how to say that.
AAVSO.
AAVSO. Here you go.
There you are.
Okay, so how can you tell about how people can get involved with that? So, I mean, because I know uh, you know, enable anyone to be part of science discovery, and as it
Mhm.
says through variable star astronomy. So, can you talk about maybe resources that are available to the public and people, how people can be part of it, and just what's going on inside of the organization?
Absolutely. So the AAVSO, let's start from the beginning. It was founded in 1911 at the
Wow.
Harvard Observatory in order to connect professional and non-professional astronomers, observers, with scientific projects. So what was happening is that there were some professional astronomers who needed data, and there was a group of individuals who were actually very used to looking at the night sky back then with their own eyes, and make measurements of stars that are changing in brightness with time. Those stars are called variable. And when we're talking about change in brightness, we're talking about brightness changes that have nothing to do with the Earth's atmosphere. So those changes are intrinsic to the stars. They tell us something about their property, and we can measure them here from Earth. So they change throughout the night, they change during a week. So these kind of timescales, right? Very short that we can measure. So this is how the AVSO in principle started, by the need of professional astronomers for more data and continuous data on specific objects. And it evolved and it grew with time, and it evolved with technology as well. So from visual observing, we added DSLR observing, we added CCD observing, we have spectroscopic observations, we're observing exoplanet transits. So anything that changes in the night sky actually is under our purview. Now, the AVSO has a lot of resources for anyone who wants to be involved, from training material. We have manuals that are actually translated in various languages. We have an online course. Actually, these are different courses that are being offered throughout the year. And they are online to reach anyone, anywhere. So people from all over the world can attend them. We have a very active peer mentoring program. So if you are an observer and you need assistance from someone to check with you whether your techniques are right, or whether the data are correct, you just want a sounding board of a much more experienced individual to help you with your own science, you can actually ask for a mentor, and we can pair you up with that individual. So we also have a very active help desk here at headquarters. We receive a lot of phone calls and emails of individuals asking for advice on their data, for advice on what to observe. We have a very active alerts program where professional astronomers, usually professional astronomers, come to us with specific targets for specific projects, and they're asking for data from our observers. So we disseminate targets of interest to individuals. We even have tools where you as an interested observer can build your own observing schedule if you want, with targets that are in need of data, stars that are in need of data, and they're visible uniquely from your location. We have actually we started a very interesting webinar series, because we found that our community is not only observers, not only individuals who are interested in taking observations or analyzing data. We have tools to analyze data as well. We found that there are individuals, our members are individuals who actually are interested in science. They want to know the answer. They want to know what's new, how the data is being used. They want to know what professional astronomers or researchers or students or anyone actually who's doing research with this data, what did they find? Why is it important? How did we learn different properties of stars? So our webinar series is focused on that, and also on our observing sections, what's happening in different parts of stellar groups, what's happening in the eclipsing binary world, what's happening in high energy, with high energy stars, but also techniques about spectroscopy, techniques about photometry, how to take data, and all kinds of things like that. All those webinars are free this year, so people should be able to sign up for free and join us. They're offered twice every month. And they're open to anyone, and they are appearing on our YouTube channel as well. So individuals who are on the other side of the world and cannot stay awake all night or wake up at 3 in the morning to come to one of those webinars have the opportunity to attend them. We also started what we call how-to hours, the first Saturday of the month, where we are focusing on specific ways or specific techniques or specific aspects of the observational astronomy. So for example, last Saturday, which was the first of the month, we were discussing how to do spectroscopy on a budget. What if you don't have $30,000 or something to build a sophisticated system to take spectra? What if you have your telescope and the small diffraction grating? How do you use that? So all those resources, all of them are free. They're on our web pages. They are available to individuals. And of course, you can always send us an email at aavso@aavso.org if you need help either identifying one of them or joining one of them or learning more about the AAVSO. Our webpage is actually our calling card. Feel free to explore.
That is good. That is great. So I think I do encourage a lot of people again to pursue this if they are already, because we kind of have this conversation, before we started recording about there's a lot of astrophotographers out there. So I think there's a lot of really great ones that already have an equipment which is in excess of 10,000, 20,000, 30, or whatever, 50,000 plus dollars, and they spend a lot of money into equipment. And it could be used for more than just, taking pictures of the universe or the galaxies or the nebula. Of course, it's fine, because that way you will inspire and encourage people to pursue, astrophotography, or somebody will say, listen, I don't want to do that. I want to do this, variable star observations, or just do anything in a science field. But I do encourage more people to pursue, variable star observations or just observations, just observing and looking, versus taking the pictures and putting them on the social media. But look, the choice is up to you. But as I mentioned, again, you have the resource. So I just wanted to clarify that for the people. Like, do you need a specific equipment? Again, for somebody who's just getting started and they have a telescope, the tracker, a mount, like how much of equipment do you need to be part of the variable star observation?
I have a pair of binoculars. That's all I have. And I've done visual observations with my binoculars. We do have a binoculars program. So you can start with as low budget as you want, and then the sky is not the limit when it comes to building an observatory, right? Yeah. You can start low budget. Yeah, actually, AAVSO has our own suite of small telescopes that are available for data collection to our members. So you can actually ask for telescope time and get the data on your computer through our resources if you want. It's completely up to you. And something, I also talk to a lot of astrophotographers. One of my good friends is an astrophotographer as well. And she's actually capturing the night sky in a way that is phenomenal. I respect astrophotographers a lot because they're bringing the wonders of the universe in front of us through their equipment. And it actually, they help us, to boldly go where no one has gone before. At the same time, astrophotography is extremely challenging. Actually, it's way more difficult than taking data on variable stars. I am serious. With variable stars, in principle, you don't have to care about clouds because, the diminishing transparency of the sky is being calibrated when you're taking comparison stars, right? You don't have to care about the moon. Of course, you don't observe a star right next to the moon, but you can go a little bit further out and take observations. Sometimes your telescope may be out of focus. It's perfectly fine. You make a measurement by increasing your measuring aperture. So as a technique, it's much more forgiving. The tools are much, much easier to use. And since individuals have the equipment anyway, what I would recommend is that, if you really want to be out and observe, it's beautiful outside, the weather is nice, mosquitoes are not there, et cetera, et cetera. But guess what? The moon is there in front of your object. You can objects of interest. You can always select a variable star to take observations. You just need snapshots, really. You don't need hours and hours of exposing in order to capture the structure of a nebula, for example. So you can do both if you want to. You can try both. And you know, the beauty with taking data on variable stars that you never know how your data are going to be used. You just don't know what that star is going to be doing. And that is, again, a part of the equation, part of the game. We collect data and we identify weird behaviors of stars based on their non-weird behaviors, if that exists with variable stars. You have to know what the star used to do in order to identify something different, something special. There's, you know, there's always something new to learn. There's always something new to discover. And do not dismiss the bright stars. Remember what happened with Betelgeuse about a year ago? Do you know that story?
What happened? No, can you tell us the story? Because I can't remember.
Oh my goodness. That was a huge excitement within both the professional and non-professional community. So we know that Betelgeuse is a variable star. Its brightness is changing by a little bit in ways that we can actually measure from here from Earth, on Earth. And actually the AAVSO database has about 130 years of Betelgeuse data that were actually observed with people's eyes or with photoelectric photometers, which is a technology that does not exist anymore. So people are actually having to maintain quite old equipment. So we knew that Betelgeuse showed certain kind of variations. It's the 5th or 6th brightest star in the night sky, depending on how you're measuring. At some point in December 2019, right when COVID started, oh my goodness, Betelgeuse started dimming, right? And you know, when it's between 6th and 5th magnitude, it's going to be brighter or dimmer, so that's not a big deal. Our observers kept observing it. But then it continued dimming and dimming and dimming and dimming and dimming. So from the point of, it was like between the 5th or 6th brightest star in the night sky, now it turned out to be the 21st brightest star in the night sky, which means that its dimming was so intense that you could see it with your naked eyes from a city. And this is where everybody started wondering, what on earth is going on with Betelgeuse? What's happening? Yeah. But the reason why we knew that that behavior was special, right, that dimming was extreme, is because we knew we had 130 years of data that showed us patterns in the brightness changes of Betelgeuse, so that when it did something weird, we said that, you know, we never saw this before.
So it wasn't a sudden change, right? It was over those 130 years.
No, the change happened within 2 months.
Wow.
Yeah. So at some point, Betelgeuse was changing on timescales of weeks to months. We knew that, but not that extremely.
So what influenced the change? Why did the change happen, and what did it cause? I mean,
and that's the $1 million question now, isn't it? Right. So we were working with a group of actually, our observers discovered it. It is individuals who do not have a PhD, right? And they alerted professional astronomers who tried to figure out whether they could take time with different equipment, the Hubble Space Telescope, for example, or infrared photometers, or even ALMA that is doing radio, to simultaneously take data. So when you are in the middle of a project like that, the first thing you want to do is take data with any means that you have in your hands. And then when the whole phenomenon recovers, whenever it recovers, I mean, Betelgeuse did not exactly call us to tell us, hey, it's going to last for a month. We didn't know, right? Then you take the data all together and you take a step back and you look at it and you say, okay, this behavior is consistent with blah. And of course, you have to actually put in the equation what you already know about Betelgeuse, right? Its size, its mass, its evolutionary stage, etc. So there were two main, there were many theories that were floating around. And of course, they had some expected or predicted results. We had to wait until April when the star actually recovered to its original brightness, to collect all the necessary data. Of course, it was like a huge international star party where both professional and non-professional astronomers were united trying to figure out what's going on with Betelgeuse. So the dominant theory right now is that Betelgeuse pretty much as a star had a dust episode. We don't really know why it did. So what happens is that it pushed dust like a big sneeze, say, in front of it that was really, really big, and it covered part of the light of Betelgeuse. And then as it dissolved, Betelgeuse kind of recovered. We know that stars like Betelgeuse do have this kind of big sneezes, this kind of dust episodes from time to time.
And what causes that sneeze?
We don't know. We have no idea. We know it exists, and here you are, more data. But that's why we keep doing this kind of research, right? Because we're trying to understand conditions under which those stars are throwing these sneezes. Are they normal? Does it tell us something about the internal composition of the stars? Even what is the composition of dust tells us something about those stars and how they evolve. So again, we're putting together a big puzzle in the universe. We're just putting together bits and pieces around different stars, but without data, we can't even fathom how this puzzle would look like, right? That's just an example of a star where we all thought, oh, we know what's going on in there. It's a bright star. We've resolved all its secrets, until we figured out that we don't have enough data to understand what's going on. Did something different? Where does that fit with the known behavior of the star?
So just looking at the data that you have currently, I mean, so what is the end for the Betelgeuse? I mean, the end is the supernova, and do you have any projections by looking back over the 130 years on when is it going to happen?
No, and funny you're asking, because that was the $1 million question. Did it go supernova? Here's the thing: we really do not know what the behavior of a star like this is before it becomes supernova. If not anything else, there's no connection between a dimming of a star or a dust episode with it becoming supernova next. We know that Betelgeuse, because it is in a specific evolutionary stage, will become supernova within the next 200,000-300,000 years, right? So you can stick around, and within the next 500,000 years, you'll see Betelgeuse as a supernova. At least that's a prediction. But at the same time, there's no connection between that episode. At the same time, there's no connection. We just don't know. So that's why we're studying this kind of stars, and we're studying similar stars to Betelgeuse to figure out how they will evolve, how fast they will evolve, what is the precursor of a supernova, etc.
Got it. So I'm pretty sure, like 300,000 plus years, there are going to be all these future astrophotographers who are going to be in a line waiting to take the first images of this beautiful nebula, after all these years. So
dare I disappoint you, because there have been lots of simulations of how Betelgeuse would look like in the night sky after it goes supernova. It's going to be very visible during daytime, etc. But it's going to be a source of light pollution at night. It's going to be brighter than the moon.
wow.
So I know, right? So it can be very upsetting for our observers.
Well, by then probably we're going to be living in some exoplanets far away from here. So hopefully.
I really don't know. I really like the Earth, actually.
Yeah, it's pretty nice. Planet. It's pretty nice, comfortable, easy to live. I don't have to wear my oxygen supply, while I'm talking with you. It's great. I like the gravity. It's not too much, so it's nice. We got used to living in here, and I think it's a good planet. But there's pretty sure there's a lot of great options too that we probably need to explore, because the planet has a timeline, which again is 3, 4, 5 billion years. Again, by looking at our star. But you talked about the data and collecting data. So again, Betelgeuse is more than 600 million light years away, I think, or 600, something like that, crazy number, right? So why is it important for us to get that data? I mean, and what do we use that data for? Is it talked about using the data? I mean, those objects are so far away, and we're talking about 300,000 years. Light pollution is a huge problem. So we're knowing that, as I said, that we're going to have this huge problem of light pollution, and Betelgeuse is going to cause that. That's great to know. Again, is that data realistic? Can we trust that data, or is it going to change over time? Who knows? Maybe. So can you talk about why is this important for us to look at the variable stars and why that data is important?
Yes. Betelgeuse is one example of what we call a long period variable, a star that is changing within very long time scales. Variable stars, their properties, the way that we observe them, the way that we study them, are actually our only chance to understand and extract fundamental properties of the universe. Have you ever wondered how we know distances in the universe? When somebody tells you that Betelgeuse is 700 light years away, do you know what that, how did they figure it out? It's not that, you took a yardstick on one side, right? And I went to Betelgeuse on the other
measuring
side.
Tape.
And measured different measuring tape, right? When somebody tells you that the sun is 5.5 more or less billion years old, how do we know? The sun did not come with a birth certificate.
Yeah.
When someone tells you that the radius of a star is like 5 solar radii, how do we know? It's not that they went there and they measured it again. So all those properties of that everything we know, almost everything we know about the universe right now came by studying variable stars. Eclipsing binaries can give you radii, and actually can give you masses if you have all kinds of observations. Pulsating stars, supernova, can give you a distance scale. Rotating variables, spotted variables, can give you age and the rate by which they rotate. There's an age-activity relationship. Even activity on the sun, right? The amount of irradiation that comes here on Earth from the sun help us understand conditions for life, at least life as we understand it, on planets that are similar to the Earth. So when we're looking for, Earth 2.0, then we could actually go and identify the right planet around the right star. You don't want a star that is so active that it's going to completely dissolve your atmosphere, or not active at all, that's going to freeze your atmosphere. So all those properties, all this information actually come from the study of variable stars. And of course, we've heard it many, many times, we're made of stardust. Stardust means stars that actually eject material. They create material in their interior, like higher metals, carbon, for example, or iron, are created at the centers of stars. And these stars are variable. So by studying them, we try to understand how this material is being created, how it comes to be in other objects around, how our own solar system was enriched with metals, how life here on Earth dependent on, this nice atmosphere that we have, how this nice atmosphere we have was created, right? How the metallicity of our planet was created. So all kinds of things like that is information we learn from variable stars. So when we're saying that, we're working with data, we collect data, etc., that data goes to become essential parts of the knowledge database that we have as scientists, as humans, when it comes to our universe. And not only that, when it comes to our place in the universe, right? How was our solar system created? How was our planet created? Why is Earth's rock made of rock and Jupiter is a big gas ball? What's the difference, right? And what will happen when the sun evolves?
Here we go. So these are, that's a great point, because again, we measure, as I mentioned, the universe by, again, observing variable stars and different stars. So that's really great. So talking about the data that you're collecting, I mean, is there a proper way? Because a lot of people, including myself, are, talking about the timelines for everything that's happening. You're talking about the scenario of, Earth 2.0 and us living again on those, planets. So is there a possible way to, to extract the data, to use that data faster again? And maybe you can talk about the process. How do you look at the data? I mean, do you use any type of machine learning AI that's being applied into understanding the data, and that way that it can be applied in the science? And maybe the ways that it can be applied in the science faster, so we can propel us faster in this 2.0 planet scenario as well?
It's very interesting you mentioning that, because humans are very impatient creatures, right? And the universe has all its time. So we have just 100 years on this little rock.
Well, we have 5 billion years, so there is no rush, I
Oh,
guess.
sure, that's an aspiration. We're going to see the planet, the sun swallowing us. There's a yes and there's a no in your question, in the sense that we are improving our techniques of taking data, but at the same time, stars don't operate in our own timelines. So depending on the stars we're studying, some data can be collected a little bit faster, some data need their time, right? It depends on the phenomena that you're studying. AI has been used a lot when it comes to data reduced from surveys, right? All those surveys that are looking at certain properties of stars within certain timescales in the sky, to reduce the data, to try to understand what kind of data they are. And because of that, one of the things we have learned is that AI, computer programs, or pipelines cannot replace the human eye. Human eyes have properties that no machine can be programmed to replicate, such as attention to detail, identifying patterns that are not there, identifying or cataloging objects in certain bins, etc. An example, you all know about the Kepler mission, right? There was this beautiful telescope that was looking at the same part of the sky around the Cygnus area for 4 years in a row. And it was observing specific stars, but for 4 years in a row, nonstop. That's the best data set ever collected, right? In that selected number of stars. And then when that data set came on Earth, it was reduced through a pipeline, etc. And some basic statistics came out. Well, the Kepler team, recognizing that, well, the pipeline is not perfect, created what they called a citizen science crowdsourcing program that was based. So pretty much what they did was they created a platform, online platform, and actually something that you could download on your phone, where they were guiding citizens, individuals, to classify those light curves and even identify missed exoplanet transits, phenomena that were weird, misclassification, etc. And as a result of that, lots of really impressive and beautiful discoveries were made on stars that were misclassified, or they were missed, or they were whatever by the pipeline. So that is just one example of how human eyes are not going to be replaced. Now, when it comes to data acquisition, the sky is huge, and we need so much data on those stars that there's no way that one aperture can capture it all. Even if you have this multi-million-dollar, super expensive, sophisticated surveys, either it's one system that is in one location, which means that it's subject to weather, subject to light pollution, the moon, subject to technical problems, or if you have multiple sites, what are you going to look at first, right? And they're also limited when it comes to the filters, the amount of light that they allow their telescopes to capture. When it comes to pipelines, I mean, really, everything is pipelined, and it goes out to the community to study. So there are always little errors here and there. One of the things that I'm constantly telling my observers is that, even all those old sky surveys and super expensive, this and that and the other one, they're not going to cover the night sky in a way that is meaningful in terms of science, not for most variable stars. And that's because they will discover a lot of interesting targets to follow up, right? And that's because they have a very limited lifetime. It's really expensive to run of the surveys, and you can't run them forever, right? So they're going to be looking at parts of the sky in very limited bunches, or they're observing one filter, one way of observing. So perhaps you need a different methods to observe the night sky. Or they, again, one site, one telescope, it's weather, right? You can't do anything about weather, especially now with climate change. The weather is changing in a way that we really don't understand yet. So we need more data even on the quote unquote known stars, right? On the, especially on the new discoveries to understand what's going on. So if not anything else, bundle up, people. There's lots of work to do. How about the next century?
Here you go, here you go. So that's what I'm trying to do here as well, to for people to understand that taking the beautiful pictures, as you mentioned, your friend does, and a lot of the astrophotographers that I have on the show, I do admire those people who work, like everybody, you know, one of them who started this hobby, because it could be the learning, you know, the learning curve is quite steep. Equipment costs a lot in most of the cases. You know, it's time consuming. You know, you have to spend, you know, your time somewhere outside, you know, it's cold or maybe it's damp, and, you know, it's not the best type of conditions, and you put in time in the post-processing, editing, you do all this work, and you put out for sometimes for people for a few likes, you know, or something like that. I mean, maybe you don't do that for that, but doing that for the science, I think you will get, you know, rewarded more if you're looking for that, or just adding more value to the society, you know, at the end of the day. So I do encourage more than a few people to look up that direction and to, you know, do variable star observations again. And of course, you're going to find all these links that you can get more information about. So again, when we're talking about that, and I love what you talked about AI, and I do understand that AI is not that advanced that it can change humans' eye, at least for now. And humans have to make their own calculations based on the way they feel, or their experience that they have, you know, like Rod Stubbings that we've been talking about. Like, no AI that existing right now can change Rod, for now at least, you know.
Or even the future.
Exactly.
No, I don't give that.
Yeah, because that's experience. That's the thing. That's, you know, common sense, the gut feeling. Like, those things is just, you know, it cannot be changed by the computer or by the robot, right? So, but can we talk about the specific objects? Like, do we have anything like prioritized, like top one, top three that you're currently paying attention to, and why is those important objects for now?
The objects that we are paying attention to right now are actually as parts of our alert system. They're objects that are very timely. They're going through some change that is evolving right now, and we need more data in order to understand it further. An example is what I told you about Betelgeuse, right? Betelgeuse became the object of the year because we needed data to understand what that dimming was, right? How did it look like? How long did it last? And what happened when Betelgeuse emerged? So right now we have a couple of objects that we're focusing on. A couple of them are novae. These are stars that suffered an indigestion after they ate a lot of material from their companion, and there's no polite way of saying that. They threw up. Pretty much, that's what they did. So pretty much they ate a lot, they could not digest the food, and they threw up. They're not destroyed, they're not dead, so they can keep eating afterwards. But what's happening right now is that we have a couple of really bright novae. Actually, one of them was discovered yesterday by one of our observers in the Southern Hemisphere in Australia. So really proud of that, and we need to understand how the episode evolves. So once the star is throwing up, then its brightness is increasing, and as that material, that ejected material, gets into the interstellar medium, it might shock, it might create dust, it might just dissolve. We don't know. This is something that we are actually actively studying. Another object that we're following is a star that actually was discovered by one of the surveys that are out there, Assassin. So that particular object was not known to be variable. People thought it was like a constant star, a star that is not really changing within timescales that we can measure, right? And suddenly it started dimming and dimming and dimming and dimming. The power of social media, my friend, we're kind of connected. So my colleague from Assassin posted it on social media, on Twitter, his Twitter account. And he said, you know, so do we know what's going on? And he kind of tagged a couple of us. And I was like, we are observing it. So we got an alert out to send it to as many people as possible. It's a Southern Hemisphere target, and it's relatively faint. But at the same time, we have observers in the southern hemisphere. So right now, as we speak, they take data to understand the eclipse. The group from the Assassin collaboration actually looked back in some of their high-val data that they had, and they discovered another eclipse, not very well covered as well as the one that we have right now. But the time in between the two events is about 12 years. And we don't really know what the two stars or two objects, one is eclipsing the other, are made of. We don't really know much about them because that star was completely under the radar. And so we are at the point where we're following that. It seems that it's emerging from its eclipse. So we have both photometric and spectroscopic data. We're doing that in collaboration with that survey. So they are taking data as well at the same time that we are. And you know what the funny part is? You know this amazing space telescope called TESS that is covering parts of the entire sky? Mm-hmm. TESS is not there right now. It's going to go there at the end of May, after the event is completed. So it's missing it completely. So if it wasn't for our observers and our colleagues at the survey, we would have missed it. And this kind of long period binary objects give us a different sort of information what types of stars are out there. There's structure even within the eclipse, which tells us that one of the objects may have a hole, maybe rings or something. I don't know. I'm making things up right now. Again, we're following it. We're trying to get as much data as we can, and then we're going to take a step back and take all the data together, try to piece a puzzle. So these are the things that we're doing right now alongside other things. Did you know that our observers are saving the Hubble Space Telescope from time to time?
Okay, can you explain us how is this happening?
How's this happening? So again, we're studying variable stars that change with time. And there is a very, very active field of science trying to understand the precursors of novae, if not anything else, right? Or systems similar to that. And what you want them to do is to actually, so in those systems, they're cataclysmic variables, the stars that I like studying. One star, there's a very, very dense little white dwarf star that is actually eating material from its companions. Stellar cannibalism, literally. You just eat its companion stars. So that is how its mass is increasing. This type of stars from time to time have burps or bursts or outbursts, that's how we call them, where the brightness is increasing by 10 magnitudes, or even they can have a nova eruption, it's like 20 times and more increase of the brightness. So if the Hubble Space Telescope is studying one of those stars, and it happens to actually go through one of these outbursts, it will bake the system. It will completely burn the detector, dead, completely dead. So what's happening in those cases is when scientists have time, telescope time on the Hubble Space Telescope to study one of those stars, they come to our community. We issue an alert and we're asking our observers to actually monitor those stars for a week before the scheduled observations happen and let us know what its behavior is in a quiescence, like a quiet level, and whether it starts brightening. Because if it starts brightening, we're not allowing Hubble to observe because it might kill the telescope. So
that's a very interesting fact. Like I never knew about that before. So thank you for sharing that. I'm pretty sure, like when we look at these, telescopes, space telescopes, just like, Hubble telescope, we think, okay, we put it out there. It's operating, and think, okay, it's just collecting data. We processing the data here in the planet. That's it. Nobody else is involved with that. We tracking, we making sure the gyroscopes are working and it's in place. It's not wobbling, and it's good. It's working. But we don't understand that it's through those collaborations, just like you're talking about now, we are able to continue to run these science projects. Yep. Again, which of course, Hubble telescope is coming to an end, and now everybody's waiting for James Webb telescope. For the next generation science, telescope, which is going to be a very, very interesting event. So you're talking about these events. So, personally, like what you would say, like of course, before Betelgeuse that you mentioned before, what will be like the top one or two discoveries that have been discovered for you before personally?
For me?
Yeah.
Before I came at the AAVSO, my research interests were a little bit more narrow than they are now. I can't even tell you right now, because every discovery and every new observation of one of those objects is exciting. It's new. We're learning something new. And even though we don't completely understand what is going on, every new star that is doing something weird is my favorite star of the day. So for example, yesterday, that nova was my favorite star of the day. Last week, that eclipsing binary was my favorite star of the day. Last year, Betelgeuse was my favorite star of the day. And actually the year before was a discovery of, in one of those novae, discovery of shocks, high energy events that were detected in hard X-rays, and they were associated with a specific pattern in the light curve of objects like that, light curve of novae at the very early stages after the eruption, which we had never seen before and we didn't know existed. Here's another little anecdote. Not too long ago, we have lots of stars in our database, right? And most of them are classified based on their known properties. So there was this one star that was classified as a pulsating variable, like a star that is changing its brightness in and out, right? Based on all kinds of data that existed. We knew it was a delta Scuti pulsator, it was there. So for some reason, about 4 years ago, some of our observers decided to take more data, right? And at some point, they discovered that there's something weird going on in there. The first order periodicities that appeared were still there, but there was something else. There was a different signal. They paid more attention to it and they said, we need different equipment. And they called the group from the UK, from Warwick, to ask them if they have access. Well, they knew they had access to a different telescope, if they had access to that particular instrument real time, and whether they wanted to take more data. So this is a case where non-professional astronomers, observers, notified professional astronomers and asked them to take observations. They did take observations, and it turned out that this was the first white dwarf pulsar that was ever discovered. It was a game changer in the field because it was a missing link in an evolution of pulsars in principle. It was predicted but never observed. And that was because a small group of observers paid attention to that one star that was misclassified in principle. And right now we're trying to identify more of these objects. It's very unique right now. But, huge discovery and change the direction of a huge field in astronomy. Now we're looking for that. Highly magnetic white dwarf, spinning like crazy. It's like a lighthouse in the universe, which we know from neutron stars, right? The usual pulsars. This is a white dwarf, it's different. So it's these kind of things that come because individuals are paying attention to their data, are pushing science forward. So again, ask me tomorrow, I may have a different favorite variable star. It's the world of science and discovery is changing nonstop.
Exactly.
That's part of the excitement.
Exactly. So it's very exciting. It's coming back to the point, as we talked about before, for somebody who's thinking about having a full-time career in a space science, again, just like you're having, it's never boring, right? It's something new every single day. So if somebody here, again, during pandemic, I know there's a lot of people thinking about changing directions, going in a different direction. And again, as you're talking about here, you don't have to have a PhD or to be a scientist in a field to be part of the variable star observation. All you have to do is to have, of course, passion for this. So if you have a little bit of passion, you looked at the stars before, you want to come back to it or continue to do that, you can be part of it. You can, look at the data. Yeah.
Yeah, and come to the AAVSO. We are offering all the resources you need, all the help you need, all the education you need, the tools that you need. We have online tools for you to actually reduce your data, do your research, plan your observations, everything that you need. We have a database full of stars. If you want to just try to analyze some of the data. And we even have a journal if you want to publish your data there. So your results of your research. So that's why we're here. We're here to help people explore the universe collectively here on the planet, with or without an astronomy degree.
Exactly, and that's very important because again, just looking at the numbers. So talking about, you mentioned, exoplanets, and we have over probably 4,000 of those that currently discovered, by different missions. So 4,000 exoplanets. And so, what do you think is the percent? And again, just looking at the variable stars and the stars out there, that would have this kind of perfect, close to 100% of chance of us living in those planets. Those are habitable zone. Are those being discovered yet? I mean, and how much do you know about that?
We have discovered candidates,
Hmm.
right? Um, and actually, those candidates are around stars that are very different than our own sun. They're around M dwarfs, which are smaller stars, no more compact, smaller though. So the habitable zone is closer to the parent star. The truth of the matter is that we don't really know which one is our perfect ideal candidate, because we're still studying not only the parent star, right, the progenitor star, but also what a habitable zone looks like for a star that has activity. Is the activity of the parent star similar to our sun? And is that habitable zone well-defined and stable? And how would a planet that has Earth-like condition will look like around a star like that? So we're still at the infancy of the really big questions, right? We spent 2 or 3 decades collecting data and trying to figure out whether there are exoplanets. They were always predicted but never discovered. Now, as you said, we have more than 4,000 counting. So at some point, we need to understand what exactly it is that we're looking for, what exactly it is that we're observing right now, and which one is our best bets to harbor habitable life like the one, organic life like the one we know here on Earth. And actually, we can look within our solar system. There are lots of beautiful, beautiful candidates that have water and they have heat around them. Look at the moons of Jupiter, right? For example, we're trying to explore Mars. And understand, again, conditions of life. This is a question that we really don't know how to tackle yet. So that's why we have all those different fields of astronomy. We're trying to explore our solar system. We're trying to explore exoplanets. We're trying to look at stars that are similar to our sun and see whether they have an Earth-like planet around them, what the period of the planet is. I mean, most of the planets we're discovering a short period. We're talking about moving around their parent star within days or weeks, maybe a month. The Earth takes a year to go around star, right? So, and at the same time, what is the composition? What should the composition be of that planet, other than atmosphere and magnetic field? What is the ratio between Earth and like land and water? Here on Earth, right, we have a certain composition, we have a certain distribution, we have a certain depth of our oceans, we have a certain heat source that comes from the interior of the Earth and from the sun. We have a certain atmospheric composition. Also, we have a certain magnetic field that's protecting us from the harmful irradiation of our parent star. So we're still at the very beginning. There's a lot of really cool stuff coming up. New big telescopes are going to provide new data and new techniques to observe those stars. And who knows what's going to be discovered in the future in terms of technology that would enable us to look at the universe in a different way, different angle.
So, do you believe that we live in this scenario which we're actually have just limited time of living on those planets? Because again, another 5 billion years plus, hopefully more, because everybody enjoys this planet. As you said, you enjoy this. I enjoy living here. So, but do you think we have to continually move from planet to planet over time because there's limited time on these stars? Is that what we have to do for the existence of humankind?
You mean the existence of humankind past 6 billion
Yeah,
years?
yeah, exactly.
Oh dear, you're trying to make me. Well, I came from Greece, but I'm not the oracle. So I honestly do not know. I think that we are in a grave danger right now already because we are abusing our resources here on this planet. So we really need to do something about that.
We could not last 5 billion years. That's what you're saying.
We will not last 5 billion years if we continue the way that we're going. We're wasting resources, we're wasting food, we're wasting, we're polluting everything. So from there on, I do not know. I really don't know. I don't know what the mentality of civilization is. You have to remember that our civilization is extremely young. We're just 10,000 years old, maybe. Yeah. So I really do not know how it's going to look like in a million years from now, if we manage to survive or something.
Again, you're absolutely right. If you look at this data that we have currently, it doesn't look very promising for the future, right? It looks like we're about to go right here, right? So do you believe we are at the moment, let's say if we are at the middle, is this possible to turn it other way around to kind of the positive outcome, or we're destined to be kind of, okay, let's abandon this planet, let's go to Mars, let's go to the exoplanet, let's start everything from scratch?
Abandoning this planet should not be a choice when it comes to improving our quality of life. We are at the point where some things can be reversed and some resources can be used much wisely if we put the energy and effort and we listen to scientists. Just listen, there are recommendations that scientists are making that could help us not necessarily reverse the damage we have done on our planet, but stop it from becoming worse. And we should all do our part, right? We should, we're talking about consuming too much plastic. I mean, how much food does a household throw? We're talking about tons of food that is thrown every year. Do we really need all that thing? Do we really need to take our own cars every day to go to work? Or is there a much more efficient way? Okay, fine. Right now, everybody's locked inside. But, just if not anything else, we should think this way, right? What can we do to preserve this planet? And, when I was growing up, we're always talking about the next generation. Well, guess what? This is the generation. We can see the effects of climate change already. We can see the effects of reduced quality of life in our everyday life. We can see it around us. We can't be blind. And no, this is not something that future generations should do. It's something that we should be doing right now. So there's a lot of resources online that people can actually find how they can do their own part. I'm trying to do my own part by trying to not create as much trash, budget a little bit my food in terms of, don't overbuy so that it would go bad and throw it away. I walk a lot. I don't know what else to tell you. I'm really trying. I know it's not enough. But if we all try and we do our best, we'll see improvements.
Exactly. That's a great point. So I do believe that everybody, including myself, should try more on that part of, consuming goods, because at the same time, we live in a time right now where, again, as I talked about, it's kind of in the middle. It feels like we're at the time where technology is here. We kind of open to other, other resources, to consuming energy and things like that. And it feels like we're educated enough to make decision. But at the same time, we live in the times where the consumerism is probably at the highest point. And we have all these companies and everybody just screaming at us 24/7 in the TV and social media, go buy, you need more. So it's really difficult, I think, for people to make that educated decision, especially where a majority of the people are emotionally unstable. That's one of the biggest problems these days because, again, of the social media. And I think it's really hard for, to tell everybody you should do this because that's going to save the planet. So the question is, how do we do that? How do we encourage the public, first of all, to understand that this is going down and we need to turn this around?
I don't have a sage advice for you. I just have, I don't think that people are mentally unstable. I think that there is such thing as
not mentally,
even emotionally unstable. I think that there's a lot of, as you mentioned, a lot of manipulation everywhere for consumerism purposes, for money, right? We're serving the gods of money. And there's a lot of peer pressure, there's a lot of societal pressure, and for some reason we are susceptible to it. It's not easy to try to be an outlier in a group that is very prone to consumerism, right? Why do I need 3 of the same, right? Why do I need to buy on Amazon every day? Stuff like that. It does take a personal effort, and it takes a little bit of introspection. Just look inside us and see what matters. You know, with the pandemic, I had the opportunity I didn't have a choice. I was just sitting inside 24/7, going out with my mask and making sure I keep social distancing. But I had a lot of time where I was not traveling. I was not running around. I usually do travel a lot, which I absolutely love. But, I had some me time. And I realized that, I could live in a much more simple way and be 100% happier than the way that I was living before. So it's a matter of personal journey for individuals. And also it's a matter of perspective. I mean, honestly, I don't really need another designer bag. Look at the universe. I'm going to live 100 years, maybe, right, on a rock around a really common star. So why is that designer bag necessary for me? Right? Why do I need to buy a new car? How is it going to improve my quality of life or affect my quality? If I don't have a car and I need one, then that's a different story. But why not spend my time to enrich my experiences, learn more about this planet, appreciate the work of others in terms of art, in terms of science, in terms of history, right? Learn more. Get experiences. That's so much different than getting stuff. And those experiences do not cost anything in terms of resources, right?
I do believe that. So this is again the big problem that we're talking about, because I know there is a huge percentage of Americans and people globally who are living from paycheck to paycheck, as people in the United States call it. So when you're living in that type of situation, it's very hard for somebody to sit down and think about, oh my God, the universe is so beautiful. I just want to go and explore and collect data. They're thinking about how they're going to feed the kids, where they're going to buy the clothes, and understand the poverty is probably one of the biggest problems. Like we have people without food or clothes, and while we're talking here on a Zoom, and we have jobs, we have things to do, we have to say, so it's a tough situation, as people who have to face. First of all, there's problems on the planet that we have to solve, and there's of course problems as the planet, or living on different planets. There's different scenarios and different levels to the problems, and we have to tackle all of them, again, with the global warming, people, poverty. So, but we have to look at all of those. But first of all, as you said, we have to start with ourselves and understand what is important for us as people going ahead in the future, which the designer bag is, it's not the case.
It might be, it's a matter of personal philosophy for individuals, and a matter of introspection and resources. As you said, there's a big poverty issue here on the planet, and not only this country, in other countries as well. So for those individuals having time, or actually being in the mindset of studying the universe, is a little bit, it's completely out of the question. They have much more serious problems to tackle. So we're not going to save society today, or we're not going to save the world right now, but we can think of how we can contribute even in these people's worlds and lives, and how we can improve our collective quality of life. Because let's face it, it's not only our actions and our situation in life that matters for quality, it's our societies. We're part of a system. So we cannot exactly say that we don't really care, right?
Exactly. Okay, so something that I want to ask you, of course, when we continue to look at the variable stars and collect all the data and go into the future, like with a lot of astrophotographers, it's a big topic that goes around right now, and probably heard about that multiple times. is the satellite debris.
Oh
So, and do
God.
you, yeah, so do you think is this a problem already, or we is going to become a huge problem for collecting that data for observatories, for scientists, for the people where we are with this right now?
It is emerging as a problem. Now, what's going to happen is a decision that is completely outside our control. I really don't know what's going to happen. It could become a major problem. I'll leave it at that.
Okay. Interesting. So again, everybody has different perspectives, I love that because I just love like when I talk with the people just like yourself, when I ask the same question and it doesn't matter, it's a scientist just like yourself or, another scientist, everybody gives different answers for some reason. One is saying, no, this is going to be the best ever. And somebody, no, it's going to ruin the planet, so it's very interesting because I think it's just come back to the same thing as I read it long time ago in a book, as I remember. They're saying there are 7 billion people on the planet. Everybody has their own perspective and everybody thinks they're right.
Yeah.
So, it's very hard. But again, if we just look at the data and analyze it, then, it's always helps.
It also depends on which data you're going to take into
Yep.
account, right? Because different data sets will tell you different things. And as humans, we are inclined to look at the information that convinces us that we are right. No one wants to be wrong, right?
Yeah.
So that's why there's so much in social media that at some point it's a headache. The approach that is taken right now with those satellites is not the best. It does have its utility. There's a reason why these kind of projects are in play, and they will have an impact, and somehow a positive impact. Depending on how they evolve, it may have a super positive impact, a super negative impact, and everything in between. So I don't want to make a prediction simply because I don't know what the big picture plan is, right? So maybe what's happening right now is like a test case. And, as part of the test case, we see trails, satellite trails, and something needs to happen with the coating of those satellites so that it doesn't interfere with our view of the night sky. Maybe it will become a failed experiment. I don't know, those satellites are not stable enough, or they have a very short lifetime, it becomes unsustainable to have them up there. They have a lifetime of 5 years. So we need to actually relaunch every 5 years, and it's becoming like a headache even for those who are sponsoring them or creating them. Maybe a better solution will come up at some point when it comes to global access to Wi-Fi, to the internet or communications. Maybe it's not going to be a problem, or maybe it's going to be a huge headache when it comes to astronomy. So forget about what we know so far. I really do not know. And I want to think positive.
Yep.
In somewhere in the cyberspace, some solution will come that is agreeable for all.
Exactly. So what other positive outcomes do you see happening in the near future? Again, as I talked about, James Webb Telescope, again, we have Perseverance right now on Mars doing the research for, some type of life form. And again, we're going to continue with having astronauts sometime in the future, continuing that research. So what else, like on a positive scale, do you see happening right now in, space agencies, private companies, or what you're working on? Like, what else is there?
Cure for COVID. I want to go visit my family again. Honestly, that would be the best thing right now, because we're all stuck inside, hoping that they're waiting for a turn to get the vaccine. I'm hoping that this pandemic will end, and will end without more victims, because far too many lives have been lost, and that is not a good thing. When it comes to science itself, I don't want to make prediction. I want to have a wish list, because predictions should be based on information, right? And I don't really know what the human mind is going to come up when it comes to technology in the future. Different ways of studying light, different ways of analyzing light, and different means of collecting data in order to boldly go, right? I would love to hear more, learn more about properties of stars like Betelgeuse. I mean, why that dust? What's happening? The thing is sneezing. Does it have allergies? And what does allergies mean in space?
I hope it didn't cause the entire COVID situation.
No, I don't think so. I don't think so. Yeah, let's blame Betelgeuse now, right? It's far away. No. Yeah. So how is life coming to be? I mean, I would love to hear more about missions that are planned for our solar system, and even see alternatives for life forms or possibility of life forms through whatever we learn from Europa and from Io, from Ganymede, from Titan, Saturn's moon, right? Or even from Pluto. Can we send more stuff out there? How on
Nobody
but
cares about Pluto right now.
Pluto, right? But it has a big heart on it, so it loves us. So all the things that we learn about our own solar system, it gives us ideas and refines the theory of how our planet fits in the big picture.
Yeah.
It's extremely important to me and extremely important to many people, because it answers a fundamental question that our ancestors had when they were clothed, when they were sheltered, when they were safe, and they looked up and they said, what is my place in the universe? Right? It's a philosophical question whose answer is based on science. So we might have the opportunity to answer that question. Of course, we're discovering all those exoplanets, right? What is their atmosphere? What does the atmosphere looks like? What is the evolution of those planets with time, right? You're studying different systems, different ages. There's so many questions, honestly, so many questions.
So
It's like,
can I just take the same question that you just said, and can I apply back to you when you talked about what is our place here on the planet? Why were you here? Again, without us being here philosophical, because I know you're a data-driven person, and I know you don't have the right answer because you said you cannot project, and but just from your way understanding things and the way we live and the way we are here positioned in the universe, do you believe, like, what's your personal belief, like why we are here? And do you believe there's something out there besides us as well?
see, that's interesting. It's a very interesting question you're asking, because beliefs and data can clash, right? Belief is very personal, and it can get
Believe
spiritual
on data
mistake.
that we have currently. Let's use that.
Even on not data that we have currently. I want to believe in people. I want to believe in their intellect. I want to believe in their kindness. I want to believe in their sense of community. I want to believe in their sense of decency. I want to believe that people can interact with each other in an equitable way. And that's the beauty here at the AAVSO. Our mission says that we are enabling anyone, anywhere to participate in scientific discovery through variable star astronomy. We're inclusive, we're diverse, we're respectful with each other. And people who are willing to interact in that way are very welcome in the AAVSO community. I want to be, I know, I want to believe, diverse voices and people that come from different backgrounds, different educational preparation, different personal aspirations, enrich science. And we're doing all those leaps, all this progress, all those leaps in technology, etc., exactly because we put our brains together. It's not one person's world. It's not one person's work. So the way I want to see it, and the way I hope that we move forward, both inside science and society, is to actually start listening to each other, start respecting each other, and provide opportunities, the same opportunities to everybody on this planet to be their best self. Does it make sense? Because I do believe that there's a little girl in the middle of the desert somewhere in a country that does not even have food to feed its own, that could be a Nobel laureate. I do believe that there might be a little boy somewhere in India, for example, is actually fighting for his life, that could be the person who's going to save us from cancer.
Exactly. I do believe that as well. But the problem is, I think, for us, we're thinking about that boy or girl, the next, again, cure for cancer, another Nobel, a Nobel Prize winner in astrophysics, something like that. And we're thinking about that person as a person who needs an internet connection, because that's what we're focusing on right now with the satellite launches. We don't think about, okay, this is the people, we need to put them in a science field. But of course, we need them to provide the internet access, because how you're going to get the education, how you're going to get the information. So look, I think we're going to reach those people. And again, part of the satellite launches, part of the people just like yourself, science communicators, because we need so many more people just like yourself who are speaking out there to the public. It's either physically, remotely, just like this, and saying, look, you can be part of this. You don't have to be a PhD, a scientist. You can be part of this, which I'm pretty sure there's a lot of educated, PhD scientists out there, but, it's through the public's effort, because we're talking about the scientists just like yourself. We're talking about this very small percentage of people, and we need so many more people. So we need public to get involved with this also, which is exactly what you're saying. So it's really great. Yeah. So guys and girls, look, that's the entire message for today for the show. I do encourage you to go to the, to the website. You're going to find all the links. Make sure to get in contact with Dr. Kafka, and again, ask her questions, how you can be part of this, which ways you can be, providing the data information. Just, get the curiosity going again, because that's what it's all about, just to get one step at a time, because look, we still have time. Maybe it sounded a little bit negative, the show, we're talking about the end of the world, and, this is going to be this. Look, the times are the way we're having and the way we're living. It's great, because I think part of that is going to be preparing us to live in a habitable, to live in Mars, where we're going to be in a habitats. You're going to be living in a domes for 24/7. So I think it's preparing a lot of people living in this type of conditions with the COVID right now. So it's all about seeing the positive outlook, as you're saying, seeing things in a positive way. Because if everything is going to end, at least you're going to end, in a positive note, and it's going to be great. So look,
I think that
sure, yeah.
if I may, the fact that we're all planning what we're going to do tomorrow showcases that we're hoping that we're going to wake up tomorrow. Yeah. So hope is part of who we are and how we are going about. What we need to do is actually just be respectful and open to our neighbors, and we're going to live our best life.
Exactly. And that's a super great advice. So look, guys and girls, last thing that I want to ask you, if you pass this episode to your friend, to your neighbor, to your colleague, to anybody, because look, if we continue to spread this message, that's what the show is all about, to inspire and encourage more people to pursue their careers in science. As I told before, a lot of people looking to transition. As we spoke before the interview, if you're a lawyer in a medical field, you can apply the same thing in a science, in a space industry as well. So look, pass this episode to your friends. And as always, guys and girls, I'll see you next time. And until then, don't forget to keep exploring.